We are on EMC conference. Please tell me what are you doing here? What was the subject of your workshop?
Yeah, so I'm here to support our Polish distributor DACPOL, selling our products, and I'm from the company Langer, and Langer is a supplier of tools for EMC pre-compliance. So our products always focus on near field, so we have different near field probes for measurements and also small burst generators, for example. And we try to reproduce failures that occur during standard tests in the near field. And in the near field, we are able to localize where the error occurs and also distinguish between which field is causing the error. For immunity, this means which field makes the electronic fails, and for the emission, it means which field is emitted. Our tools help finding the source and defining the source of error in more detail to then implement the correct and the needed modifications on the PCB to then don't fail again in the EMC standard test.
What's the most important thing for designers to understand EMC? What's your experience?
So most important is that you have multiple components on the PCB, ICs, connectors and everything, and it's not always the ICs are the reason for the failure. It's mostly the layout and the environment the ICs are working in. So when you have multiple bad layout decisions, I can have a robust IC that still will fail. And this also is the case for connectors, interfaces, and for the whole layout of the PCB. We have multiple products here. Here we have two boxes with our near field probes, which can detect electric or magnetic fields when placed over a PCB. Those products are small burst generators. We are also able to generate errors on the PCB. And when we make a better layout decision, like the lower trace, we are not able to influence it anymore. And besides this, we also have whole development sets. And for example, here we have our E1, which is a whole set for troubleshooting immunity problems. Here's a small generator, and this is a burst generator. And the main difference to a standard burst generator is that it's not a metal housing, and we have two outputs. So we have here a differential output. It's possible to test different paths of the current through the electronic. For example, when I connect the generator to an electronic, I can now test different paths of the disturbance through the electronic to see when the electronic fails and the electronic is doing the same failure pattern than in standard test that was failed. So really a big advantage. It's also possible to take these small near field probes to the generator to localize exact regions where immunity problems because of, in this case, magnetic field occurs, but we also have electric field problems for searching areas that are sensitive to electric field. And the main idea behind this is when I'm able to reproduce the same failure pattern with this generator, the same pattern I had in the standard test I failed. I can distinguish between the fields, so if magnetic or electric field is causing the error, and where it's located. So these are two really important information I need before making modifications on the PCB. The second set we have is a development set for emission, and this set always comes together with our tent. So in the tent there is a metal base plate where we put this current transformer. This current transformer is connected to a spectrum analyzer and is measuring the current that would be emitted in far field. As an example, when I connect the electronic to a cable, and I have, for example, emission problems in megahertz range or in hundreds of megahertz range, then this whole setup is my antenna that is emitting the electromagnetic field. The antenna is not the trace itself, because it's too short. The resonance frequency would be in high gigahertz range. And the current that is floating in this antenna and is generating the emission in the far field can be measured with this current transformer. This means when we connect this current transformer to a spectrum analyzer, we will get the same emission spectrum like we are getting in a far field measurement with an antenna. And this makes it much more easier to see if a modification was a good idea or a bad idea. If a modification really helps improve the emission, or if it doesn't help. Because when we start sensing magnetic fields, you will always measure more magnetic fields than the magnetic fields that are really relevant for the emission. Yeah, and that's where this current transformer and this ESA measurement principle comes into action. End of the year, we will also introduce our new product, the Troublestar, which is also pre-compliance burst generator, exactly like this one, but it has some more advantages. This one has a pulse rise time of 4 nanoseconds, which equals the rise time of a burst pulse. This generator will have a rise time of approximately 850 picoseconds, which equals the rise time of ESD. So things we can do with this generator, basically reproducing failure patterns from burst test, will be possible for ESD tests with this generator. And also here the voltage is not generated by relays, which is the reason for the clicking noise of the black one. Here we have a MOSFET switch who's generating the pulse voltage, which means it's constant voltage that can be set to defined value. This is also the second main advantage of the Troublestar, which will be released end of the year.